Hi everyone, welcome to another video. Today I would like to discuss the manipulation of Taylor series. So we covered Taylor series, we covered the Lagrange error, and now we are ready to make full use of Taylor series and start applying them. Now I'd like to start applying them by trying to perform some calculus on these different series and apply the Lagrange remainder as well as some of the other tests that we covered in previous videos. And then after this, we only have a couple more videos left in Unit 9, and then we're off to Unit 10. All right, let's get started. So we only have an example today, so we'll keep it quick. So I would like us to evaluate the integral from 0 to 1 of e to the negative x squared dx to within an error of 0.001. Now, e to the negative x squared is a very important function because of its applications to probability. So it looks like this. It is the famous bell curve. So it's called the normal distribution or the Gaussian distribution is a riff off of the function that we have here, e to the negative x squared. It's very important in probability. The only kicker is that it's not, we can't integrate it. And that's a big problem because this is a probability density function, and to find the probability, you need to be able to integrate it. So, what we are going to do is we're going to try to integrate it right now, and we'll see if we can get a good error, or, well, a low error. Anyways, so the way that we can do this is we can represent e to the negative x squared as a Taylor series. So we know the Taylor series for e to the x, so we know the exponential is equal to the sum from n equals 0 to infinity of x to the n over n factorial. So what we can do is we can make a substitution, say that x here is actually equal to negative x squared. So then we get the sum from n equals 0 to infinity of negative x squared to the n over n factorial. Okay, we can clean this up and turn this into a nice alternating series that we like the looks of, and we get the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial. All right. So now we are prepared to integrate this. Now, as we covered, the linearity of the sum allows us to perform the integral right inside, or right outside, if you will. So we get the integral. We're just going to take an antiderivative for now. The antiderivative of e to the negative x squared dx is equal to the antiderivative of the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial dx. All right, so what we can do now is we can perform this antiderivative by taking out all the constants that we don't need and just performing an integral on the x to the 2n term. This gives us a nice expression. We get the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 times n factorial. All right, that should make a lot of sense. Now, what we need to do is we need to perform this integral definitely. So we set our bounds at 0 and 1. We apply the fundamental theorem of calculus. Thankfully, the 0 term cancels out. So we get the form 1 minus a third plus a tenth minus 1/42 plus 1 over 2/16. And we go so on and so forth. We're going to stop here at 1 over 2/16. And we are going to find what that's equal to, which is 0.7475. So now all we need to do is we need to plug this into the alternating series remainder theorem. So that says that we are going to make sure that the next contribution is smaller than our error. So the next contribution to our sum would be 1 over 11 times 5 factorial per this formula here. And that is equal to 1 over 1320. That 1320 is less than 0.0001. So that means that we've estimated our value of this integral between 0 and 1 to within, 3 decimal points. All right, that's all I've got for today. In the next video, we are going to cover applications of Taylor series to physics. And then we are going to be off to polar curves and parametric equations for our final unit. Thanks for watching, and we'll see you in the next one. Bye.